Hey everyone, welcome. Today, we're diving into something fascinating, the generative pre-trained transformers, also known as GPT. This tech wizardry has turned text generation into something incredibly cool. So let's hop in and explore what makes GPT tick. This lesson is focused on understanding the text generation using GPT. I'll talk about how it's changing the way computers understand and create text. Awesome. Let's roll. So let's look at some basic stuff. So generative pre-trained transformers is a state-of-the-art transformer-based model developed by OpenAI. These here are some descriptors for for what people call GPT as. It's called language model, generative AI, artificial intelligence, chatbot, transformer. For our use case, we will consider large language model or a language model. So what is a language model? A language model is a model of language. It produces a probability distribution over some vocabulary. So GPT is a state-of-the-art transformer-based model developed by OpenAI. It uses their pre-trained knowledge to predict and generate the next words. So let us imagine that we had a task of predicting the word in the sequence I am. So if I give the neural networks the word I am, what of all words in English is the most likely word to follow? That at its very core is what GPT is trained to answer. So how it does is it has a vocabulary of around 50,000 words. It gives you the likelihood for every single word that follows I am. So for the phrase I am, it will give the probability for words like happy, sad, school, Bjork. So there are lots of ways how I am happy, I am sad can go. And you add a little bit of randomness, and all of a sudden you have a language model. You have a language model that can write essays, that can talk and do a whole lot of things. It's like having a never tiring assistant who can churn out ideas and drafts at an impressive pace. So let's look how it actually works. So to write essays and all, the model needs to understand the context. So how does the contextual understanding work? Let's talk about the incredible power of contextual understanding in GPT models. Imagine a text generator that not only produces coherent text, but also nails the tone, style you want. GPT models do just that, thanks to their innate ability to grasp context. They understand the flow of conversation, enabling them to generate text that seamlessly fits the given context. But how do they do it? Well, GPT employs a unique technique called causal self-attention. Unlike its predecessors, BERT, which uses bidirectional context, GPT models only look at the preceding tokens during training. This helps the model stay coherent and it generates text sequentially. And that's not all. Positional encodings are added to differentiate words with similar meanings but different positions. This enhances the model's contextual grasp even further. For example, imagine you're texting your virtual friend ChatGPT about a movie. GPT will understand if you're chatting about a plot twist, a romantic scene, or an action sequence. It infuses the right context into its responses, making your conversation natural and engaging. Let's look at attention mechanism. This mechanism allows the model to weigh the importance of different elements in the input data. In other words, it helps the model focus on relevant information while downplaying irrelevant details. Think of attention mechanism as adding pathways from the encoder to the decoder, as you can see here in the diagram. This enables the decoder to directly access important input features from the input text. But how does it work? Each word in the input sequence is associated with three vectors: a query vector, a key vector, and a value vector. Let me explain it to you with an example. Think about a virtual assistant that helps you summarize a long article. The attention mechanism acts like a highlighter, identifying key sequences, sentences, and important information in the text. It ensures that the summary is relevant and captures the essence of the article, highlighting crucial details and omitting less relevant parts. This way, the summary remains concise and informative and contextually relevant, just like the attention mechanism in GPT models. Now, let's talk about attention heads. These are what makes the attention mechanism work. These are like the secret sauce that makes the attention mechanism even more powerful. So instead of tackling the entire sequence at once, attention heads selectively focus on specific words or a phrase that are crucial for understanding the context. Each attention head specializes in learning specific relationships and dependencies between tokens in the input sequence. How does it work? Well, for a particular token's query vector, the attention head calculates a similarity score with the key vectors of all the tokens in the input sequence and gives you a probability of similarity scores for every word in the sentence. It basically tells us which word is more important than the other words in the sentence. It helps the GPT models with a nuanced understanding of context, allowing them to comprehend intricate nuances, relationships, and significance within a given text. So this is about one attention head. Let's look at multi-head attention. Here, multiple heads are introduced, multiple attention heads are introduced to generate attention masks for embeddings of sentences. This creates multiple contexts for the same sequence. Imagine having a same sentence, but multiple interpretations of that sentence. That is what multi-head attention does. One attention head builds up an understanding of the sentence, one understanding of the sentence, and then um, multiple heads build up on that. So uh, we have multiple attention understandings of a single sentence, and this helps us to contextualize the sentence and get what the intent of the sentence is accurately. So each of the values, key queries, each of key query and values gives us 3 output instead of 1. These 3 key queries now give 3 different weights from each of the attention head. These 3 weights then get multiplied. We perform matrix multiplication with these 3 values to get 3 multiple outputs, and then we select the best output from those. So that is how the attention mechanism works in a GPT model. So now let's look at how the training process is actually performed for training a GPT. There are 2 phases for the GPT training process. First is the pre-training phase, which we are going to look at now. In the pre-training phase, a GPT model learns to predict the next word by training on extensive text data without labeled tasks. It involves a few key steps. Tokenization. The input text is divided into smaller units called tokens. These tokens can be as short as a single character or as long as a word. Then we also consider the positional embeddings, adding positions to the tokens. GPT models don't have an inherent understanding of the order of words in a sequence, right? To overcome this, positional embeddings are added to the token embeddings. These embeddings encode the position of each word in the sequence. Then we use self-attention mechanism. As we saw previously, the attention heads and the multi-head attention are used to build a self-attention mechanism. Then the transformer layers. GPT models consist of multiple layers of self-attention and feed-forward neural networks. Each layer refines the model's understanding of the input by considering different levels of context. Then we also use masked language model, which is basically during the training procedure, a portion of the input tokens is randomly masked out, and the model is tasked with predicting that masked tokens based on the surrounding context. This helps the model to learn contextual representations. This concludes the pre-training phase. Then we go on to the fine-tuning phase, where the after the pre-training process, the GPT model is fine-tuned for specific tasks. This involves training the model on a smaller data set that is labeled for a specific task, such as language translation or text completion or question answering. The fine-tuning process adapts the pre-trained knowledge to specific task at hand. Let's look at what is included in the fine-tuning phase. So we need task-specific data. A labeled data set for the desired task is prepared. For example, if the task is sentiment analysis, the data set would contain text samples paired with their corresponding sentiment labels. Then we also fine-tune the architecture of the GPT. The pre-trained GPT model is used as the base architecture. Then the task-specific data is used to fine-tune the model's weights through backpropagation. Then we also fine-tune the loss function depending on the task, such as classification tasks use cross entropy. Then we also perform optimization, such as gradient descent, or a similar optimization algorithm is used to update the model's parameters based on the loss calculated during each iteration of fine-tuning. That's how the GPT models are trained. Let's look at a demo of how we can build our own GPT model. Here, I've included a script. Here, I've included a script which is going to help you understand the basics of the GPT model. So first of all, we import dependencies. So here we're going to be using PyTorch to build a GPT model from scratch. This model is based on the paper Attention is All You Need by Google, which was released in 2017. First, we have imported the dependencies. Then we are defining some hyperparameters here. These hyperparameters will be used to build our final language model. Here we can see we are using batch size, which explains how many number of sentences are we going to take for like in a single batch. Then we have defined block size, which is the length of the sequence that we are going to consider. Then these are some normal generic neural network training hyperparameters, such as iterations, evaluations, then learning rate, dropout rate. Here, there's also these three might be new, which are embeddings, heads, and layers. So what embeddings are, those are the representation of a single word. So if there's happy, we have, so if we have a single sentence, we are creating 64 dimensional embeddings for that sentence. Then we have heads. So we looked at attention heads. So we're going to be using 6 attention heads here. And then we have number of layers. So number of layers is the number of transformer blocks we are going to use. Here in the GPT architecture, we saw that there are multiple transformer blocks. So these are the number of layers we're going to be introducing in our GPT model. So let's, here I am using the data set of, it's a script from the show Game of Thrones. It was imported from Kaggle. I've uploaded it to my GitHub for easy download. So we have loaded that script, which contains like dialogues of every character from all the seasons in a scriptural format. So we have imported that, and then we have created 2 functions here, which are the encode and decode functions. So let's look at those, which these functions help us tokenize the input. Here, I've created a short demo of how the tokenization works. So we imported all the text into characters. Then we calculated the length. The length is basically the vocab size which we are considering. So here you can see percentage, numbers. So these were present in the text. So we have built a vocabulary using that. And then we have defined the functions encode and decode to take the input words and convert them into numbers, because computers don't understand words. So we converting them into numbers. Here, for the input string hello there, we're getting an encoded integer output. So here you can see for hello there, it has generated an array of the integer representation of it. Here you can see that it has decoded E as 53. Here also you can see in there, the E is represented as 53. So that's how the encoding and decoding is working here. So this is a very basic type of tokenization. For our use case, we're going to be using this. Then we have defined a function get batch here, which is going to help us get the data in batches. Then we also have broken down the training data and validation data, which is standard practice in training neural networks now. Here, we have defined a loss function, which calculates the loss value between the ground truth and the predicted truth by the model. And we are optimizing that loss to get a better, to fine tune our model. So let's go further. Here, I've defined the attention head. As we saw in the main mechanism that helps GPT to be useful is the attention mechanism. Here, I've defined the head class. It is defined to build the attention mechanism that will provide us with probabilities for every sequence. So if I have demoed you, I've initiated a random sequence. So this might be a sentence or might not be a sentence, but I have generated random variables, and then I feed it to the attention head. The attention head gives me the probabilities for every word. So that's how the attention mechanism works. It gives priority to the word which is more important. More higher probability is given to that word which we need to focus on. Then we build the multi-head attention mechanism. Here, multiple attention heads are used to get the complex contextual nuances from the input text. As you can see here, we defined number of heads in the hyperparameters above. So here we are using the head function to build multiple heads to get multiple contexts for a given sentence. Then it's fed into the feed forward network. For every key, value, and query pair, this multiple head will give us multiple different weights. The output from multiple attention blocks are concatenated using this feed forward network. So let's break it down simply. We have attention head, then we have multi-head attention. So we use multiple heads, attention heads in the multi-head attention. And then we use multiples of multi-heads to build a network. So then we have the transformer block here, where we use multiple of those multi-heads into our block. As you can see in our GPT architecture, so here in the transformer architecture, we have multiple attention heads. See here, multi-head attention, and then all of them are combined into the transformer block. So let's build a GPT language model now. We have defined all the components that we need for our language model. Now let's start with our GPT language model. So here we use all those bare bone components and build the GPT model, and use some standard neural network procedures such as weight initialization, okay, to here we have used all the transformer blocks and the components to build our GPT model. Now let's look at the model training here. While training, I have here the parameters our GPT model is trained on. So the dimensions and embeddings and heads decide how much million parameters does our model have. So here my model has only 300,000 million parameters, which is trained on. Here, my loss is very bad because I haven't fine-tuned it um, to learn the task yet. So after the training, we have defined a generate function here in our language model, which helps us get the next word, which generates the next word in our sequence. So let's try to generate text now from our GPT model. So first we load our trained GPT model, then we give a seed sequence, what we want to be our input sequence, and then the model should predict the next words for it. So here I've given Arya Stark, I want to meet Ned, and then I have, so the output from the model would be numbers, right? So we need to decode those. So we have decoded those, and we are given here a max number of new tokens, which is 3000. So it's going to predict the next 3000 words from the given seed text here. So now after we print it, we see that it's printing the script properly. It's getting the names right, like Tyrion Lannister here. Some of them are not correct as well, but our model has learned that the word structure, but not the sense of what's happening, the storyline yet. Here, some of the words are just gibberish. So as this model is only trained on 300,000 parameters, we can say that it cannot write a new script for our season 8 of Game of Thrones. So that's how the training is. This concludes the code. To increase the performance of this model, fine-tuning is necessary. Such fine-tuning includes increasing parameters or giving a large corpus of data. This can help the GPT model learn the intricacies of human language. And then it can like properly give us the dialogues by Bran and build a better context and conversations for us. So I'll give you a best example I've seen of fine-tuning is when we say uh, the jump of understanding from GPT-3 to GPT-4 happened. I bet you all have used the ChatGPT, right? But the ChatGPT-3 model was built to predict next words in the sequence, the next tokens from our input text. While GPT-4, what the engineers did was they uh, used the GPT-3 understanding of generating the next tokens and then fine-tuned it on a data set of questions and answers. So it created the context of answering questions when the input was a question. So this helped ChatGPT-4 to be extremely better than ChatGPT-3. So these models like GPT-3 and GPT-4 are trained on billions of parameters and are changing the landscape of how we learn and we code. So I hope this lesson taught you how the text generation in GPT works. And we covered all the basic concepts of how GPT models work. And now you know like how your friend ChatGPT works internally. You can use the script to generate your own ChatGPT model from scratch. If you have a better computational power, then you can train it on your own data set to generate whatever you want. So that concludes my lesson. Thank you so much, and see you soon.